Am I audible? Yes, I think others are still joining. So let us wait for a few minutes. As I said earlier, we have finished this Bayesian network, and now we will move to the next topic. So while we are waiting for others to join, maybe 1 or 2 minutes, please ask me if you have any questions or doubts. We may discuss anything in general. We can spend this right time to spend at this juncture to discuss about your understanding of machine learning, and if you want to discuss something related to machine learning, not just what we have discussed, but in general also. Yes, Anish, I will share the note. So maybe you are reading something else, or you are also discussing with someone about machine learning, and you might be wondering what can be done in machine learning and all that. So we can spend some time at this juncture to discuss that. So are there any specific query or thoughts that you want to share here? Okay, then let's begin with the next part. So initially, I thought that we'll jump to unsupervised learning. We had seen Bayesian network as an example of supervised learning, and then we start unsupervised learning. But in between, I think before we go to unsupervised learning, there is a very important and powerful topic of machine learning, which is called dimensionality reduction. So this time, I feel like we can first take that part. It has some very interesting mathematical foundation, and this dimensionality reduction techniques are something that we use for all kind of machine learning models. So be it supervised or unsupervised. So it can be used with naive-based classifier. It can be used with decision tree classifier. It can be used with clustering and all that. So we'll spend some time on that. I will share slides, or but before that, let me give you idea of what dimensionality reduction is. So you know what is dimension, right? In machine learning, what is dimension in context of machine learning? It generally says column. Yes, the features or attributes that we are dealing with, which makes column in our data set, are called dimensions. And we often talk that in a huge problem there are hundreds and thousands of dimensions in the data, and it takes a lot of time to train the model. So now, if the dimensions that we have selected are not good enough, then the machine would not be trained properly. So training, as you know, the training is as good as the data set that you expose the model to. And if the data set is not good, then training will not be good. And dimension is key part of the data set. So if you train on unnecessary dimensions or unnecessary features, then your machine learning system would not be trained properly. So that's why it is important to choose dimension wisely. And that is the part of machine learning called feature engineering. It is also a job of machine learning experts to decide important features on which the model can be trained. So we'll discuss about this feature engineering today. It reducing the benefit. It could also obvious and you realize by now the benefit of reducing the dimension. So one benefit is the training time will be less because lesser the data after the training. So you can do training faster if the dimensions are reduced. And the second thing is that if you train on important features, then your overall training will be better. So let us see. So keep this thing in mind. We do not want to. So to summarize whatever we we want to with less number of features, and we want to find out the important features from the new data. So that task is task of dimensional reduction. Okay, so keep this in mind, and now we'll move to. I will share the screen, and we'll move to some bit of linear algebra. Very interesting part. So this is what I mean by dimensionality. There are six features as shown here in the data: x1, x2, x3, x4, x5, x6, and when the feature in 1, 2, 3, 4, 5, 6 example here is as shown here. Like first example is 1, 6, 2, 1, 1. Second example is 2, 5, 4, 1, 1. For example, is 3, 4, 4, 6, 1, 2. Fourth example is 4, 3, 5, 8, 1, 1. Fifth example is 5, 2, 6, 10, 1, 2. And sixth example is 6, 1, 7, 12, 1, 1. So this is a small data set. Now let us see whether the features that we have shown here are good enough or not. What are the issues with the picture? As you see, just how strange value. For example, 100, so if you see X6 feature has most of the value 1, 2, 1, 2, 1. There is only one value which is not consistent with the other value, which is 100. This value is the outlier. That is problem with feature X. If you look at feature X, then all values are same. It means that you cannot discriminate between the examples, or you cannot distinguish between the examples based on feature X5. X5 is also not. If you get X3 and X4, then you would set the progression will say like X3 is 1, 2, 3, 4, 5, 6, 7. X4 is 2, 4, 6, 8, and 12. So both are progressing with the example value. And similar for X1. In fact, if you compare X1 and X1 plus 1, is in the family to the full set and is x2. So it is x1 into, if you look at x4, it is x1 into 2. X3 and x4 both are actually uh, sublinear functions of x1. And x2, if you look at x2, then x1 and x2 are going in opposite direction. While one is increasing, another is decreasing. So these are some immediate inspection that every machine learning engineer has to do by looking at the data. And based on that, they can decide whether the features are good or not. So out of these 6 features and the brief story that we discussed about those features, how many features you would use to train the model? Any answers? Out of this x1, x2, x3, x4, x5 and x6, which one you will keep and which one you will remove? Yes says that we will keep x1 and x6. Okay, I have already marked the cross here, but I hope you got the point also. So do you all agree with this answer? Vishrut, yes, Chanil, all are saying the same answer, that keep x1 and x6, remove x2, x3 and x4. Okay, so more or less the answer is correct, and it is intuitive also, not a big thing. But the important part is now this we have done through visual inspection and our basic understanding of mathematics. But if you want to write programs for this, like you give input as data and get output as reduced set of features or some other dimensionality reduced data. So in that case, what are the mathematical tools we have? So let us talk about those tools also. So one example is this x1 is equal to, and let's talk about feature number x5. x5 is 1, 1, 1, 1, 1. And we said that is not useful because all values are same. But if you want to write a program, then do you know any statistical function which can tell you that this is not useful? Answer is on your screen, and that is standard deviation. Standard deviation of x5 is 0. Right? Mean minus. I believe you remember that. X5 minus mean x. So every value minus mean. So 1 minus 1 will turn out to be 0. So standard deviation can tell you, and also variance. Variance is square of standard deviation. So there is no variance in the data. We can say that variance of x5 is very less. Variance of x5 is very less, and that is why it is not useful. So you want a feature for which variance is good. Okay, that is one part. Generally saying it is about correlation matrix. Okay, we'll talk about that also. So variance can tell you that x5 can be removed. How do you decide that x3 and x4 can be removed? So that is linear function. Yes. So this linear function also. And if you want to look at it differently, then that can be done through something called covariance. So the way we calculate variance is a change of value in the column, while covariance is calculating the difference of value between the columns. So between every pair of features, we can calculate covariance. And if you see that x1, x3, and x4 has very high covariance. How do we calculate covariance? Covariance can be calculated as this. The formula is similar to the formula of variance, which is on the right side of the screen. Xi minus x bar square upon number of example minus 1. Formula of covariance is up between two features. So one is xi and second is xj. And xi minus the average of xi or mean of xi, xj minus mean of xj divided by total number of samples. That will be covariance. So if both are covarying, then what will happen? Both will increase or decrease together. So if both values of xi and xj increase or decrease together, then we call high covariance. If one is increasing, other is decreasing, then you will see very low or negative covariance. And if there is no relation between their growth, or their growth is not related, or change of value in both features are not related, then you will see zero covariance. So we look for very low or zero covariance. So these are the three standard mathematical tools: variance, standard deviation, and covariance variance, which can do this primary inspection of data, and you can write programs based on this to see how good or bad your data is. I think one thing I missed talking about is outlier. How do you calculate, or how can you write a program, which mathematical function out of this variance, covariance, and standard deviation you would use to calculate outlier or to find out outlier? I think yes, deviation, as most of you are saying. Daniel, Dave, yes, all agree to that. Standard deviation. As we have discussed in our class also, standard deviation decides how far the data is from mean. Right? And here we know that mean is somewhere between 1 and 2, and your data 100 is very far from mean. So standard deviation can tell you that this is an outlier. And there is a box plot drawing technique also based on this, which can help you in detecting outlier from the data. Okay, so that was a period or basic talk about how to look at the data set as a statistician to figure out usefulness of data. To move further from here, we need to recall our old friends, vectors and matrices. Just a second. So we'll recall our old friends whom we know as vectors and matrices, which you might have studied in your linear algebra courses also. Okay, Janil says, can we scale down the column also? Yes, so that we do that. We do that scale down and all. So what we do is we remove the mean from the data set. We scale the data into one range of 0 to 1. Yes, all these things we need to do. But for now, let's focus on these vectors and metrics, which you all know. So my narrative of or my understanding of vector and matrix is something like this. So if vectors are superhero, then matrix is Thanos. What do I mean by this is, in some random Marvel universe, of course for the geek like us. So let's say 1, 2 is a vector. Vector is 1, 2. And matrix is 2, 3, 3, 4. So what happens when you multiply this vector V with a matrix A? When you do A cross V, I think you all know this multiplication, right? It will be something like this. 2, 3, 3, 4 multiplied by 1, 2, which turns out to be 8 and 11. So 2 ones are 2 plus 3 twos are 6, 8. 3 ones are 3 plus 4 twos are 8, 11. It becomes 8, 11. So we all know this, how to multiply vector and matrix. So, but if you see this on a graph, then what actually we have done? What we have done is, so this was the vector V. This poor vector V was originally sitting over here. And after you multiply it with A, after we multiply it with A, it has lost its space and direction and everything, and it has moved to this. So this is your new matrix. Let's call it V prime or something like that. So that's why I say that this only purpose why the matrix are born is to torture vectors. Right? So the matrix, whenever a vector is multiplied by matrix, or whenever a matrix hits a vector, vector will lose its position and move somewhere else in the space. Right? So that's why I said that in this Marvel universe of geek, the vectors are kind of superheroes and matrix is Thanos. But is that whenever there is a Thanos, there is some superhero who can beat Thanos also, right? So there is always a vector who will not be affected by the matrix. So even if the matrix hits the vector, nothing will happen to that that vector. You name vector. Of course, name is on what we should call the title of this is eigenvector. So eigenvector is a kind of superhero who can beat Thanos also, who can beat this matrix also. So for every Thanos, there is Iron Man, and that Iron Man for us is eigenvector. And why I'm saying this? Because if you look at the formula of eigenvector, it will be something A into V is equal to lambda into V. So vector is our original poor vector. Now it is 0. You can be Thanos also. So V is Thanos, V is Iron Man. And when Thanos hits Iron Man, what happens? V means V. It does not change. It does not go anywhere in the Thanos becomes poor scalar lambda. The matrix disappears, Thanos disappears, it becomes a simple scalar function. And the vector V is our Iron Man, and that Iron Man is called eigenvector. So this is very old mathematical the linear algebra theories that was somewhere in early 20th century. And this was one part here. Usually the mathematics or mathematicians do this kind of equations and do research through mathematical proofs. Often not really what will be the applicability or how this will be used. But somehow after 50 years of this, as the computers are in and processing learning develop, people have found out a beautiful application of this discussed now. But the point that I'm trying to make is either those kind of rather fully matrix within eigenvector. So हर से सवाल होता है something like this. Fully matrix you get eigenvector, and when you multiply that matrix with the eigenvector, that will not change its position or direction in the space. Because in the same direction, can scale the value through lambda, but the point in the same direction. Very useful for any application of this in the kind of machine learning and image processing and all these subjects that we are discussing. So one position is whenever you are transforming an image. Right? So whenever you are working with graphics, you have some canvas, you have some pictures, and you do some operations on that picture in game programming or image processing or in any kind of skill. So where you want to keep the direction same, you don't want to change the direction, the pointer remains same. So in that case, you make sure that the vectors that you are playing with are eigenvectors. So that you scale the image, when you want to scale the image from zoom in, zoom out of the image, then image should not rotate or change its position, it just scales down. So in that case, eigenvector is useful. So there is an interesting application of eigenvector where you can do scaling, but the directions will not change. All pixels will be in same direction. Are you with me so far? Any questions on this? Is the story clear? Any question on this? Okay, I think Urjit says clear. Okay. Okay, then let's take an example, a quick example of how to calculate eigenvector and all that. Though I think you have done this in your mathematics course, but it's a good time to revise that. So let us say A is a matrix of -6, 3, 4, 5. A is the matrix. And we want to find out eigenvector for this matrix. So how do we do that? If you remember the definition of our eigenvector, formula is AV is equal to lambda V. AV is equal to lambda V. So if we use that equation, it will be AV minus lambda V is equal to 0. So similarly, A minus lambda I into V is equal to 0. So we want to find out a V for which A minus lambda I into V is equal to 0. So A minus lambda I is 0. Let's do that. -6, 3, 4, 5 minus lambda 0, 0 lambda is equal to 0. So -6 minus lambda 3, 4 into 5 minus lambda is equal to 0. And simple algebra here that -6 into lambda into 5 minus lambda minus 12 is equal to 0. So lambda square plus lambda minus 42 is equal to 0. And lambda 1 is equal to -7 and lambda 2 is equal to 6. From this lambda we can calculate V as follows. AV is equal to lambda 1V and lambda 2V, both vectors we can calculate. So -6, 3, 4, 5 V1, V2 is equal to -7 V1, V2. Again, make two equations out of that. -6 V1 plus 3 V2 is equal to -7 V1. 4 V1 plus 5 V2 is equal to -7 V2. And that gives us V1 is equal to -3 V1. So the first eigenvector V1 is -3 1 is equal to -7. And similarly, we can calculate second eigenvector as 1 4 for the eigenvalue lambda 2 is equal to 6. Right? Are you with me? Any question on this computation? Okay. So these are the two vectors we found. And if you see where they stand in the two-dimensional space, then 1 4, the first vector we had found was 1 4, is pointing here. And second vector is -3 1. And if you notice, all eigenvectors are always orthogonal to each other. That is also a property of eigenvectors you might have heard in your mathematics or linear algebra course. So they are always perpendicular. So if you are dealing with data, here we are dealing with data of two dimensions, so we could find out two eigenvectors. So number of eigenvectors is equal to size of the matrix. So if you are working with an n cross n matrix, then you can find out n eigenvalues and n eigenvectors. Here we took example of 2 cross 2 matrix. So we have 2 eigenvalues and 2 eigenvectors. If you are working with 3 cross 3 matrix, then you can find out 3 eigenvalues and 3 eigenvectors. Again, all eigenvectors are perpendicular to each other. And if we see our original data point where it is lying, then the original data point means the matrix was -6, 3 and 4, 5. So let us try to see where they are. -6, 3 was somewhere here, right? And 4, 5 was somewhere here. Right? So both eigenvectors are pointing to the data item. So usually these eigenvectors point to the data across which the points towards the matrix data points points towards the direction of the matrix data point. That will be a better way of saying it. So we'll refine this understanding. But for now, keep this in mind that for an n cross n matrix, you can find out n eigenvalues and n eigenvectors. And these eigenvalues and these eigenvectors are orthogonal to each other, and they point in the direction of the data. And depending upon the eigenvalue, you can find out the importance of the eigenvector. We'll talk about that more clearly, but right now keep in mind that depending upon the eigenvalue, we can decide importance of eigenvector. So an eigenvector with higher eigenvalue is more important than the eigenvector with less eigenvalue. Right? So eigenvectors can serve as axis to study data points. That is one takeaway from this. So originally our data was on this red colored axis, instead of that, now we have found out two new axes, which we call our eigenvectors. So these are our new axes to study the data points. And there are certain benefits of doing this, which we will exploit in the coming lectures. We will discuss some algorithms which makes use of this. But for now, eigenvectors can serve as axes to study data points. Along eigenvectors, the data points are not distorted. This is very trivial statement at this point. We'll see what it means with very concrete algorithm. But it usually points along the direction of data points. Then eigenvectors point to the direction along which the variance is maximum. Again, this also we will see usage technique, and this is where the eigenvectors becomes useful for machine learning people. Right. So this is the story of eigenvector, revision from what you already know from probability. But I will again wait for a minute or two. Please ask me if you have any doubts on this. Any questions? So is this clear? Chandresh says, yes, I will share the slide. Yes, Chandresh, I will share the slide. Maybe today only I will upload all the material. And also I am trying to prepare notes which can be useful to you. Okay, so now let's talk about combining eigenvectors with covariance. So this gives us a very powerful dimensionality reduction algorithm called principal component analysis. Let's see what it is. We will begin it and we will finish it in the next lecture. So we talked about dimensionality reduction. We talked about variance and covariance. We talked about eigenvalues and eigenvectors. So these are the prerequisites to understand the algorithm that we want to discuss. The algorithm name is Principal Component Analysis, which we briefly know as PCA. The Principal Component Analysis algorithm, it uses covariance to compare features. As we had seen in our earlier example, we want to compare the features and find out the useful one. It uses eigenvectors to find dimension of high covariance. So on the features, it will see that in which dimension the data is covariance is high, and in that direction it will point us. So we know that those features can be removed or kept. So let us see how it works. So x1, x2. Let's again talk about two features only, x1, x2. Let's keep our discussion to two dimensions. So there are two features, x1 and x2, and they have three values. So first example is 1, 2, second example is 2, 3, and third example is 3, 4. So these are our three data points, 1, 2, 2, 3, and 3, 4. So first thing we do is we calculate we calculate covariance of this data point x1 and x2. So how do we do this? So covariance formula is x1 minus mu x1 square into x2 minus mu x2 square and x1 minus mu x1 into x2 minus mu x2. So this table can calculate both covariance and variance. So first let's calculate mean of x1 and x2. So mean of x1 is 2, mean of x2 is 3. So x1 minus mu x1 is minus 1, x1 minus mu x1 is minus 1, 0 and 1. And x2 minus mu x2 is again minus 1, 0 and 1. So what does this initial inspection tell us? The covariance between the data is very high, isn't it? Both are co-varying. So we did this mean removal, and now let's calculate variance also. So x1 minus mu x1 square is 101. That is 2 by 2. So variance is 1. And x2 minus mu x2 square is 101. 2 by 2, that is 1. Variance of both data points x1 and x2 is 1. Let us now see what is covariance between x1 and mu x1. That is x1 minus mu x1 into x2 minus mu x2. So minus 1 into 1 is 1. 0 into 0, 0. 2. So again 2 by 2. Covariance is also 1. It is the covariance. And we put covariance. So positive covariance is both features are increasing or decreasing together. Zero covariance means that not related. And negative covariance means that one is increasing and another is decreasing. So let's look at covariance. So this x1 and x2 covariance matrix is something like this. So this point is variance of x1. The top left entry x1 is variance of x1. Bottom entry in the diagonal or bottom right is x2. There is variance of x2. And top right and bottom left are variance between x1 and x2, and they are same, right? So there is 1, 1. So this two-dimensional representation of variance and covariance, which we have calculated, is called covariance matrix. So let us see what we achieve by doing this covariance matrix. So if you see, our first point was one, 2. Our first point was 1, 2. Second point was 2, 3. And third point was 3, 4. So 1, 2, 2, 3, and 3, 4 were the 3 data points, right? And this was x1 axis and x2 axis. If we do principal fault analysis and find out eigenvector of this covariance matrix, we will get this red line. These are eigenvectors actually. In our context, we call it principal components. So it will point along the line of data, and the data along the eigenvector along which you get the maximum data is component. You see how we get this. out so far, just to make sure that you got the point. If the PC1 the way that is your diamond process, then in which case will be then also about two components, the two I vector and for time vector, diagonal will be larger. So what is your vector? I will correspond to PC larger or eigenvalue corresponding to PC2 would be larger. Any suggestions, any ideas? Okay, they would say PC1. Okay, and why PC1? Do you think that eigenvector related to PC1 would be larger? Because data points are along that vector. Data points are along that vector. So it is larger eigenvalue. Really. Let us see the computation we will know. So what we do is co we find value error co-estimate. Not really, it will be like this. It's like 0 and 1 comma 1, 1 comma 1. Here, it will give these two axes, P1 axis and P2 axis. Anything along 1 comma 1, there are more data points left, and for negative value is also larger too. From P2, which is 1 comma number learning along and I will do test. So what we have done, what we have achieved is to find out the principal component from the program is the new dimension. We have dimensions 1 and 2. Now the new dimension are then principal component which are actually eigenvectors. And there's the label the name, principal component, and we got these two vectors and we also carry that which vector or which axis are dominant for data point or better captures the data point, better captures the relative data compared to the. Because if you look from PC2, then all three data points are in other same point. But if you look from PC1, then you see that data point values are different. So PC1 can separate data than PC2. So we can conclude that to understand this data point, 1, 3, and 4, only sufficient. You want data and process that and another dimension. That is principle dimension technique. For whenever there are n components. This is point to direct hypercoding. The eigenvalues decide the importance of principal component. Higher eigenvalues indicate better spread of data along the principal axis. The principal component with low eigenvalue can be removed to reduce number of dimensions in the data point. So that's the idea of principal component. And if you want to put down the algorithm instead, it will be something like this. First step is remove mean from data. Second is calculate covariance. Third, find explain matrix. These eigenvectors in a descending order of eigenvalue. And remove eigenvectors with low eigenvalue to reduce number of dimensions. Right, so that is story of principal components and how principal components can be used to reduce dimensions in the data. I will stop here and I will wait if you have any questions. So please ask me if you have any questions. We have 2 or 3 minutes to discuss. Any questions? Because if there are no other questions, I will stop here. Thank you.